Most people grow up with a clear mental picture of an atom. There is a tiny core at the center, and around it, much smaller pieces travel in tidy paths, much like planets circling a star. This image is simple, memorable, and easy to draw, which is why it appears in classrooms, books, and museums around the world. Unfortunately, it gives a deeply misleading idea of how atoms actually work. The real structure of an atom is not just slightly different from that picture. It is fundamentally unlike anything from everyday experience. To understand why, let's begin with the simplest possible atom, hydrogen. It contains one proton and one electron. The proton forms the nucleus, and the electron is somehow associated with it. The familiar picture suggests the electron is at a particular location at any given moment, moving along a predictable path. But modern physics tells us this assumption is wrong at the most basic level. An electron does not have a definite position until it is measured. This is not due to poor instruments or lack of precision. It is a property of nature itself. Before measurement, the electron is described by a mathematical object called a wave function. This wave function does not tell us where the electron is. Instead, it tells us the likelihood of finding the electron in different places if we choose to look. In some regions, that likelihood is high. In others, it is low. In certain places, it is exactly zero, meaning the electron will never be detected there. It is tempting to imagine the electron as a tiny object hidden somewhere within this probability pattern, waiting to be discovered. That idea is also incorrect. According to both theory and experiment, the electron does not secretly occupy one location before measurement. The wave function is the complete description. Only when a measurement occurs does the electron appear at a specific point, detected as a single localized event. This immediately rules out the idea of classical orbits. If an electron truly traveled around the nucleus like a planet, it would be accelerating continuously as its direction changed. Accelerating electric charges emit energy in the form of radiation. As a result, the electron would rapidly lose energy, spiral inward, and collide with the nucleus in an extremely short time. Since atoms are stable and clearly do not collapse this way, electrons cannot behave like orbiting particles. What about the opposite idea, that the electron simply sits still near the nucleus? That also fails. If an electron were motionless at a precise location, both its position and its momentum would be exactly known. Quantum mechanics forbids this. The uncertainty principle states that certain pairs of properties, such as position and momentum, cannot both be sharply defined at the same time. This is not a statement about experimental limitations, but a fundamental rule of the universe. So the electron is neither orbiting nor stationary. Instead, it exists as a quantum state described by a wave function. Certain wave function shapes are allowed, and these stable patterns are known as orbitals. An orbital is not a path or a trajectory. It is a three-dimensional map of probability. The lowest energy orbital in hydrogen is spherical, with the highest likelihood of detecting the electron near the nucleus and a gradually decreasing likelihood farther away. Higher energy orbitals have more complex shapes, elongated regions, rings, or multi-lobed structures. But these shapes represent probabilities, not physical objects. When an electron changes energy, it does not move smoothly from one orbital to another. It transitions abruptly. One moment it is described by one wave function, and the next moment by a different one. The change is instantaneous, with no intermediate state that can be observed. We can calculate when these transitions occur and measure the energy involved with remarkable accuracy. But we do not have a classical explanation for how the change happens. The nature of the electron itself adds another layer of strangeness. In some experiments, electrons behave like localized particles, producing single impacts on detectors. In others, they spread out and interfere with themselves, creating patterns characteristic of waves. The electron is not truly a particle or a wave in the everyday sense. It is a quantum entity that does not fit into classical categories. Its behavior depends on how it is observed, and its full description again comes back to the wave function. Measurement plays a central and puzzling role. Before measurement, the wave function evolves smoothly, spreading and interfering like a wave. During measurement, the outcome is always a single, definite result. The wave function appears to collapse into one possibility. How and why this happens remains one of the deepest open questions in physics. Many interpretations exist, but none change the practical success of the theory, which continues to match experimental results with extraordinary precision. When we consider atoms with more than one electron, the picture becomes even richer. All electrons are fundamentally identical. There is no intrinsic label that distinguishes one from another. This indistinguishability leads to powerful consequences. Electrons obey the Pauli exclusion principle, which states that no two electrons can occupy the same quantum state simultaneously. This rule forces electrons to fill different orbitals and energy levels, giving rise to the structure of the periodic table, chemical bonding, and the solidity of matter. Without it, all electrons would collapse into the lowest possible state, and the complex world we know could not exist. The nucleus, often imagined as a cluster of tiny solid spheres, is also far from simple. Protons and neutrons are themselves composite objects made of quarks bound together by the strong nuclear force. The mass of a proton does not come primarily from the masses of its quarks, which are very small, but from the energy of the fields that bind them together. In this sense, much of what we call mass is actually stored energy, organized into stable patterns. Stepping back, a striking picture emerges. An atom is not built from solid pieces arranged in space like parts of a machine. It is a dynamic pattern formed by interacting quantum fields. These fields extend everywhere, and what we perceive as particles are localized excitations within them. The apparent emptiness inside an atom is not truly empty at all. It is filled with fluctuating fields and probabilities. Even properties like size and rotation challenge intuition. Experiments suggest that electrons have no measurable size, yet their quantum states extend over a region much larger than the nucleus. Electrons also possess an intrinsic property called spin, which behaves mathematically like angular momentum, but does not correspond to literal rotation. Spin can only take certain discrete values, and its behavior defies classical explanation. Energy within atoms is also quantized. Electrons can only occupy specific energy levels, much like a vibrating string can only produce certain notes. When electrons move between these levels, atoms emit or absorb light at precise wavelengths. This is why each element has a unique spectral fingerprint, and why quantum theory can predict these patterns with astonishing accuracy. Trying to probe atoms more closely only reinforces these limits. To resolve very small structures, we need high-energy probes, but those probes inevitably disturb the system. At the quantum scale, observation is not passive. Measurement changes the state being measured. Properties such as position do not exist in a definite form until the act of measurement brings them into being. So what is truly inside an atom? Not miniature planets, not solid particles, and not tangible substance in the everyday sense. What lies at the foundation is a mathematical framework, wave functions, quantum fields, and equations that describe how probabilities evolve. These abstract structures do not resemble anything from ordinary experience, yet they give rise to everything we see: matter, chemistry, life, and thought itself. The lesson is not that the universe is unknowable, but that it is profoundly different from our intuitions. By following the evidence and trusting the mathematics that consistently shows us, we gain a deeper appreciation of reality. The atom, far from being a simple building block, is a reminder that nature is subtle, surprising, and far more intricate than any picture we can easily draw. The atom, far from being a simple building block, is a reminder that nature is subtle, surprising, and far more intricate than any picture we can easily draw. And once you truly accept that idea, something interesting happens. You stop trying to force atoms to behave like familiar objects, and instead you begin to ask a different kind of question. Not, what does an atom look like? But what does an atom do? And how do we describe it? That shift in thinking is where real understanding begins. Because at the deepest level, physics is not about pictures. It is about relationships, patterns, and predictions. The equations of quantum mechanics do not tell us what an electron is in a visual sense. They tell us what outcomes are possible and how likely each one is. And remarkably, that is enough to build the entire physical world. Consider chemistry for a moment. When two atoms bond to form a molecule, nothing like tiny hooks or glue is involved. What happens instead is that their electron wave functions rearrange themselves into new patterns. These patterns lower the total energy of the system, making the combined structure more stable than the atoms were separately. A chemical bond is not a thing. It is a shared quantum state. The molecule exists because the mathematics allows a stable solution that includes both atoms at once. This is why chemistry works at all. It is why molecules have shapes, why proteins fold in precise ways, why DNA carries information, and why life can exist. None of this requires electrons to follow paths or particles to touch one another. It all emerges from the way quantum states combine and constrain each other. Even temperature, something that feels very physical and immediate, has a quantum foundation. What we experience as heat is the collective motion and excitation of enormous numbers of particles and fields. At the atomic scale, temperature corresponds to how energy is distributed among available quantum states. As energy increases, more states become accessible. As it decreases, fewer remain available. Absolute zero, the coldest possible temperature, is not the absence of motion, but the lowest energy quantum configuration allowed by the rules of nature. Now think about solidity. A table feels solid. A wall feels solid. Your body feels solid. Yet, as we've seen, atoms are mostly open space, and their components never truly touch. The sensation of solidity arises from electromagnetic forces and the exclusion principle working together. When you press your hand against a table, the electron clouds in your skin and the electron clouds in the table resist being forced into the same quantum states. That resistance manifests as pressure. What you feel is not contact but force, fields pushing back against fields. This also explains why objects do not pass through each other under normal conditions, and why matter has structure. Without these quantum rules, the concept of a rigid object would not exist. There would be no stable shapes, no persistent materials, and no distinction between one object and another. At this point, it becomes clear that classical intuition fails, not because we are bad at imagining atoms, but because atoms do not belong to the classical world at all. Classical physics is an approximation, a simplified description that works when dealing with large numbers of particles averaged over time. It emerges naturally from quantum mechanics in the same way that smooth curves emerge when you zoom out far enough from a jagged surface. But it is not fundamental. This realization also changes how we think about causality. In everyday life, we expect events to have definite causes leading to definite effects. In quantum mechanics, the best we can do is calculate probabilities. The theory does not say which outcome will occur, only how likely each outcome is. And this is not due to ignorance or hidden variables that we have yet to discover. As far as experiments can tell, randomness is built into the fabric of reality itself. That idea is uncomfortable. It challenges the belief that the universe is fully deterministic, that the future is completely fixed by the past. Yet, despite this randomness at the smallest scales, large-scale behavior remains astonishingly predictable. The laws of thermodynamics, fluid dynamics, and classical mechanics still hold because randomness averages out when enough particles are involved. Order emerges from uncertainty. Time itself acquires a new perspective when viewed through this lens. At the quantum level, most fundamental equations do not prefer a direction of time. They work equally well forwards and backwards. The familiar flow of time, from past to future, emerges from statistical behavior and the tendency of systems to move toward more probable configurations. The arrow of time is not imposed by the microscopic laws, it arises from them. Even space is not quite what it seems. In quantum field theory, particles are not objects sitting in space. They are excitations of fields that exist everywhere. Space becomes a stage filled with potential activity where fluctuations constantly appear and disappear. What we call empty space is simply space without long-lived excitations, not space devoid of structure. This view has profound consequences for modern physics. It underlies technologies we now take for granted: semiconductors, lasers, magnetic resonance imaging, atomic clocks, and quantum computers. These devices work not in spite of quantum mechanics, but because engineers have learned how to harness its strange rules with precision. Atomic clocks, for example, rely on the exact frequency of transitions between quantum energy levels. These frequencies are so stable that they lose less than a second over millions of years. GPS satellites depend on this precision. Without quantum mechanics, modern navigation would not function. Quantum computers take things even further. Instead of bits that are either 0 or 1, they use quantum states that can exist in superpositions. This allows certain calculations to be performed in ways that have no classical equivalent. While the technology is still developing, it is a direct demonstration that quantum behavior is not just philosophical. It is practical. And yet, despite all this success, there remains a deep sense of mystery. We can calculate outcomes with incredible accuracy, but we struggle to explain why the universe works this way. Why probability is fundamental, why certain symmetries exist, why the laws of physics take the form they do. These are questions that physics can pose, but not yet answer. This is where curiosity becomes essential. The goal of science is not comfort or familiarity. It is understanding, even when that understanding forces us to abandon cherished intuitions. The history of physics shows a repeated pattern. Each time we push deeper, the universe turns out to be stranger, more abstract, and more subtle than we expected. The atom, once imagined as a tiny solid object, dissolves into a network of fields, probabilities, and constraints. What remains is not emptiness, but structure of a different kind, mathematical structure. Equations that describe how possibilities evolve, rules that limit what can and cannot happen, patterns that persist because they are stable solutions to those rules. And from those patterns arise everything familiar: light and matter, stars and planets, chemistry and life, thought and consciousness. The world feels solid and continuous because, at our scale, quantum uncertainty is hidden beneath layers of collective behavior. But it is always there, quietly shaping reality. So when we ask what an atom really is, the most honest answer is this: an atom is not a thing you can picture. It is a process, a stable arrangement of quantum fields, governed by laws that do not resemble everyday experience, yet give rise to it. It exists not as a tiny machine, but as a solution to an equation. That may feel unsatisfying at first. We naturally want reality to be made of tangible pieces, something we can imagine holding in our hands. But nature is under no obligation to match our preferences. The deeper we look, the more we find that reality is written in a language of mathematics, symmetry, and probability. Understanding this does not make the universe cold or empty. If anything, it makes it richer. The fact that such abstract rules can produce a world filled with color, texture, sound, and meaning is extraordinary. From the quiet mathematics inside an atom emerges everything we know. And that, perhaps, is the most remarkable lesson of all. The universe does not need solidity at its foundation to be real. It needs only consistency, structure, and laws that allow patterns to endure. Out of that, reality builds itself, one quantum possibility at a time.